All right. Hello and welcome back. This is the System Design Interview book by Alex Zhu. And fortunately, I have found my microphone. So, hopefully, from now on, we would have a better quality in terms of the audio quality. Uh, let's continue from what we have left before. We have gone through the four first chapters. Now we are on the fifth chapter. We kind of uh, passed the 25% of this book. So hopefully we will finish this and we will learn a lot during this process. So the chapter 5, design consistent hashing. So to achieve horizontal scaling, so that's a little bit too zoomed in, okay? To achieve horizontal scaling, it is important to distribute requests per requests data efficiency and evenly across servers. Consistent hashing is a commonly used technique to achieve this goal. But first, let's take an in-depth look at the problem. Before continuing further, let me pick my marker, and now let's just change the color a little bit to, let's say here, yeah. Okay, purple. Yeah, it's really nice color. The rehashing problem. If you have n cache servers, a common way to balance the load is to use the following hash method. Okay, like you have n cache servers, like you have 1, 2, 3, 4, up to nth cache server. Okay, a common way to balance the load is to use the following hash method. The server index is going to be the hash key mod n, which is the remainder of dividing by n, where n is the size of the server pool. So we have a server pool, let's say we have a server pool of 4, but the hash of the key mod the n, which is the server pool, which is 4. So let's see what we get. Let us use an example to illustrate how it works. As shown in table 5.1, we have 4 servers. Okay. Wow, great. I just said 4 and it came out 4. Okay, hash mod 4. As shown in table 5.1.5, we have 4 servers and 8 string keys with their hashes. Okay, so we have the key 0, key 1, 2, 3, 4, 5, 6, 7. And we mod the hash by 4. So the hash here is 18, 35, 86, 17. So if you mod it by, if you divide it by 4, you get the remainder of 1. So if you mod it by 4, you either get 0, 1, 2, or 3. That's how mod works. If it want to be 4, then because it will be divided fully by that, it becomes 0. So we have 1, 0, 2, 0, 1, 3, 2, 3. As we can see, we have modded the hash key and we got some repeated values. Okay, like 1 is repeated 2 times, 0 is repeated 2 times, 2 is repeated 2 times, and 3 is repeated 2 times. So we have evenly distributed the keys among the hash that we got. To fetch the server where a key is stored, we perform the modular operation. F of key mod 4. For instance, hash of key 0, the key 0 is this value, okay? So this hash, modding 4 means dividing by 4 and taking the remainder of that, becomes 1, and 1 means a client must contact server 1 to fetch the cached data. Okay? Figure 5.1 shows the distribution of keys based on table 1.5. So the distributions are, as I said, evenly distributed. Server index 0, 1. This is a fully functional cache server. Okay. And let's say we have like 7, 8 keys, and based on each key, we will be redirected to server 0 to server 3. Okay. This approach works well when the size of the server pool is fixed. Okay, like we have 4 servers, and the data distribution is even. Yeah, and the data, as we saw here, when we kind of divided the hashed value of them by 4 and took the remainder of that, so evenly they got the same number of keys associated to them. So yeah, and the data distribution is even. However, this is the however part. Problems arise when new servers are added or existing servers are removed. Okay? For example, if server 1 goes offline, if it's a server 1, I guess he or she means server 2, which has the name of server 1, goes offline, the size of the server pool becomes 0 using the same hash function. We get the same hash value for a key, but applying modular operation gives us different server indexes because the number of servers is reduced by 1. We get the results as shown in table 2.5 by applying the hash mod 3. Now, since we have 3 servers, now the n becomes 3, and we see we will get 3 zeros, 3 ones, and 1 2. So it is so obvious that it is not evenly distributed. We have 1 key goes to 1 server, and the other keys go to those 2 servers. So figure 2.5 shows the new distribution of keys based on table 5.2.5. So as you see, we have the overload of data going to server 0, a little of overload to server 2, and we have kind of underloading the server 3. As shown in figure 2.5, most keys are redistributed, not just the ones originally stored in the offline server 1. This means that when server 1 goes offline, most cache clients will connect to the wrong servers to fetch data. This causes a storm of cache misses. Consistent hashing is an effective technique to mitigate this problem. Yeah, the problem was that I didn't consider that the key 0 is stored in, okay, where were that stored? Yeah, it is stored in server 1, and 4 also is stored in server 1. And apart from these 2 that, yeah, normally shouldn't have any response, the other keys, the orders that have, these servers have the answer for them. But if we have this way, so we kind of here this way, like 2 on 6, and we want to just show the value of key 4 in server 2, that we don't have that value available. Also in server 0, we have key 1 and key 3. We only have key 1. So key 3 is wrongly distributed to server 3. So that's also the problem. I was considering this, that all servers have the same key value of all the keys. They all have the value for all the keys. They are kind of the replica of the cache server, but here it is saying that I thought that this was the load balancer, but this is these are meant to be only for the caching system. Like this had the purpose of serving to certain keys, and this had the purpose of serving to another certain keys. So if we wrongly distribute the keys to the servers, so we won't get the answer or we won't get the value for those keys. I assume that we all are familiar with what is the cache, what is the cache server, like a Memcache and Redis, and probably the file one, but we are all familiar with the key value pair kind of storing and retrieving the value from the cache server. As shown in figure 2.5, most keys are redistributed, not just the ones originally stored in the offline server. This means that when server 1 goes offline, most cache clients will connect to the wrong servers to fetch data. This causes a storm of cache misses. Consistent hashing is an effective technique to mitigate this problem. Yeah. Okay. Consistent hashing. Quoted from Wikipedia. Consistent hashing is a special kind of hashing such that when a hash table is resized, okay, and consistent hashing is used, only k divided by n, k of n keys need to be remapped on average, where k is the number of keys, okay, the number of keys, and n is the number of slots. So, okay, so let's calculate that. When the hash table is resized, we resize it down, okay, the k number of keys and the n number of slots, okay, only them need to be remapped, okay. It means not, yeah. So it basically means all of them except the ones that are missed, as far as I got this understanding of this. In contrast, in most traditional hash tables, a change in the number of array slots causes nearly all keys to be remapped. Actually, this also was all keys to be remapped. How do you say this is not? Keys to be remapped, where k is the number of keys, okay, all number of keys, and all number of slots. Okay, let's see. Hash space and hash ring. Now we understand the definition of consistent hashing. Let's find out how it works. Assume SHA or SHA-1 is used as the hash function f. Okay, SHA-1 is used as the hash function f, and the output range of the hash function is x of 0, x1, x2, x3, up to xn. In cryptography, SHA-1's hash space goes from 0 to 2 to the power of 160 minus 1. That means x0 corresponds to 0, xn corresponds to 2 to the power of 160 altogether minus 1. And all the other hash values in the middle fall between 0 and 2 to the power of 160 minus 1. Figure 3.5 shows the hash space. So this is the hash space from 0 up to 2 to the power of 161, which I guess is pretty large value that cannot be kind of calculated so easily probably, but yeah, that's a lot of numbers. Okay, all right, so we consider that. By collecting both ends, we get a hash ring as shown in figure 4.5. So if we take this and attach it to the x of n, it probably forms a circle, okay, and this would be the x0. If we go through all the path, and reach back to the beginning minus 1, that becomes the x of n, which is 2 to the power of 160. Okay, so let's consider this. Hash servers, what are they? Using the same hash function f, we map servers based on server IP or name onto the ring. Figure 5.5 shows that 4 servers are mapped on the hash ring. So let's say we have 4 servers. Server 0, f of server 0, okay, will give us the server 0 location. 1, 2, and 3. The hash keys. One thing worth mentioning is that hash function used here is different from the one in the rehashing problem. And there is no modular operation. As shown in figure 6 of 5, here, this one, okay, 4 hash keys, key 0 up to key 3, are hashed onto the hash ring. So the keys are also hashed onto the hash ring, okay? So we use a kind of hash algorithm that if we give the key to that, if we give anything to that, it gives us a position in the hash ring. So yeah, so we have basically the server address and also the keys addresses on the hash ring. So let's see what comes next. The server lookup. To determine which server a key is stored on, okay, to determine which server a key is stored on, okay, like this key, all right, has the server stored for it in here. To determine this, we go clockwise from the key position on the ring until a server is found. Like we go with here. Let's walk through. Go. It's a long journey. Go ahead. And oh, we got here. Okay. So here it says basically this is the server for this hash key. Figure 5.7.5 explains this process. Going clockwise, key 0 is stored on server 0. Key 1 is stored on server 1, as you see. Key 2 is stored on server 2. And key 3 is stored onto server 3. All right. So add a server. Using the logic described above, adding a new server will only require distribution of a fraction of keys. In figure 5.8, after a new server 4 is added, which is the 5th server, only key 0 needs to be redistributed. Let's see why. Why is that? Because server 4, when it's added here, okay, so we would say like the key 0, which has to be mapped to server 0, will be mapped to server 4, since we said that the first server that you match from clockwise path is going to be your server, the key. Okay, we talk to the key. After a new server 4 is added, only key 0 needs to be redistributed. Key 1, 2, and 3 remains on the same servers. Let's take a close look at the logic. Before server 4 is added, key 0. Yeah, before server 4 is added, key 0 is stored on server 0. Now key 0 will be stored on server 4 because server 4 is the first server it encounters by going clockwise from key 0's position on the ring. The other keys are not redistributed based on consistent hashing algorithm. Okay, so I kind of am missing something, but anyway, it says this key 0 is redistributed to server 4, and now this is valid. The previous one is invalidated probably based on what I got so far. So I really just want to know what happens to the server 0, but let's see. Remove a server. When a server is removed, only a small fraction of keys require redistribution with consistent hashing. In figure 9.5, when server 1 is removed, okay, only key 1 must be removed on server 2. Must be remapped to server 2. The rest of the keys are unaffected. So here it says, yeah, these are here. Okay, if you imagine that from this we got to this stage, like server 1 want to be removed. If this is the scenario, then the only thing we need to do here, this was the K2, this was the K3. So probably K1 needs to be remapped to server 2, and probably K2 needs to be invalidated. So let's see. Yeah, this one is kind of removed. This one is mapped to this, but before that, this one is invalidated probably. Yeah. Two issues in the basic approach. The consistent hashing algorithm was introduced by Karger et al. At MIT. The basic steps are map servers and keys on the ring using a uniformly distributed hash function. Okay, we want to map servers and keys on the ring using a uniformly distributed hash function. So this uniformly distributed is the key here. To find out which server a key is mapped to, okay, to find out which server a key is mapped to, go clockwise from the key position until the first server on the ring is found, as we saw here. Two problems are identified with this approach. First, it is kind of impossible, okay, to keep the same size of partitions on the ring. Let me see, okay, that the microphone is not turned off. Okay, so two problems are identified with this approach. First, it is impossible to keep the same size of partitions on the ring for all servers, considering a server can be added or removed. The same size of partitions. I guess he means like we have 1, 2, 3, 4 partitions. But it says it is impossible to keep that. I guess it means this, but I'm not sure. Yeah, to keep the same size of partitions on the ring for all servers, considering a server can be added or removed. Yeah. Probably this analogy was the one that I guessed was correct. Okay, probably. It is possible that the size of the partitions on the ring assigned to each server is very small, okay, or fairly large. It is possible that the size of the partitions on the ring assigned to each server is very small or fairly large. Yeah, probably here. This is somehow small. This is not small, but somehow. And this partition is fairly large, so it means that. So the distance between the key and the server is could be fairly large or small. Okay. In figure 10.5, if S1 is removed, S2's partition highlighted with the bidirectional arrows is twice as large as S0 and S3's partition. Yeah. The analogy that we had was correct. So from this one, server 1, if it is removed, so the partition from here to here, actually the partition is kind of calculated from server to server, okay, but this partition is twice the partition of 0 to 3 and 3 to 1, 3 to 2, okay, so they are not evenly distributed in this way, in this manner. So if S1 is removed, S2's partition highlighted, yeah, is twice as large. S2 partition is twice as large as S0's and S3. So S0's partition, actually it is calculated from where it stands, going counterclockwise, and S3 where it stands from counterclockwise until each of them reach another server. So that's the partition, I guess, here now. Second, it is possible to have a non-uniform key distribution on the ring. For instance, if servers are mapped to positions listed in figure 5.11.5, most of the keys are stored on server 2. However, server 1 and 3 have no data. Okay? Most of the keys are stored on server 2. Oh, yeah, I think I'm kind of getting it more now. So here, from here up to here is the partition for server 2. Why? Because we get a server, go counterclockwise, and we reach another server, which is server 1. So based on this, from here to here is the partition that the keys can be mapped to the server 2. Yeah, and it said one of the problems is that if it has a fairly large partition, so it could take all the space available to them, kind of most of the space available to them, and the keys cannot be evenly distributed to other servers. Like there is one server, like server 3, that has no keys associated to that. So there is actually no key here that based on that key, we could map it to the server 3. And server 0 is also, server 0 also has only one key associated to that. And by the way, they have fairly kind of smaller kind of smaller path and fairly little volume of data associated to them. So this means that server 2 would have really high load, while server 3 would have fairly low server loads, and also server 1 as well, because if we take that and go counterclockwise, we also have no keys associated to that. So, and even if we have lots of keys distributed here, so compared to what space server 2 has available to that, it is fairly small. Yeah. A technique called virtual node or replicas is used to solve these problems. Okay. All right, so let's see what virtual nodes is. It is. A virtual node refers to the real node, and each server is represented by multiple virtual nodes on the ring. Okay. It is kind of referring to the real node, and as it said, each server is represented by kind of multiple virtual nodes on the ring. So in figure 12.5, both server 0 and 1 have 3 virtual nodes. The 3 is arbitrarily chosen. Okay, that kind of just is making sense to me, you know. At first, I didn't get what the ring is, but now it is kind of making sense. And yeah, I kind of am getting it. So we have probably only 2 servers. Yeah, server 0 and server 1. And if we, let's say this is the ring, this is, by the way, this is a very bad ring. Server 0 here could end up being here. And let's see, server 1, server 1 could end up being here, let's say. Okay, so if this is the distribution area, so the kind of distribution area that the server 0 has, if we go not clockwise but counterclockwise, we see a very small area is assigned to server 0, so it means it can handle fairly small number of keys to be kind of associated to that server. But server 1, if we go counterclockwise up to server 0, we almost get like 95% of all the keys in this system will be associated to server 1. So just for having a fair distribution, we say, okay, we have server 0, yeah. So distributed with some virtual nodes. So let's take server 0 and respawn all the virtual nodes. Like spawn it probably will come here and here. And for server 1, let's write down 0 and 0 here. Let's see. And for server 1, we say, okay, distribute it again. So the chance of having fairly large area or large volume of keys associated to that will reduce dramatically. And if we kind of calculate the amount of space associated to the keys to each virtual kind of virtual nodes, it will be kind of really near. It is not equal, but it will be near 50%. So it is more fair to have probably 3, 4, or some number of virtual nodes associated to that, to have fair number of hash keys available to that. Okay, and in real world system, the number of virtual nodes is much larger. Yeah, like they say, okay, let's have 10 virtual nodes. Instead of using S of 0, we have S of 0 sub 0, S of 0 sub 1, and S of 0 sub 2 to represent server 0 and the ring, on the ring. Similarly, S of 1 sub 0, S of 1 sub 1, and S of 1 sub 2 represent server 1 on the ring. With virtual nodes, each server is responsible for multiple partitions. Yeah. Partition edges with label S0 are managed by server 0. On the other hand, partition with label S1 are managed by server 1. So this partition is for server 1. Sorry about that. I have kind of sore throat. Okay. So this partition is for server 1, and also this partition is for server 1. Imagine this was for server 1 and this was for server Imagine this was for server 0 and this was for server 1. So we would have that I told you, like 95% for server 1 and only 5% to server 0. But now this area along with this area and also this area is distributed for server 0. So it is more fair. Probably it is like 45% compared to 55%. And the server loads are kind of managed by this approach. To find which server a key is stored on, we go clockwise from the key's location and find the first virtual node encountered on the ring. In figure 13.5, to find out which server K0 is stored on, we go clockwise from K0 location and find virtual node S1 sub 1, which refers to server 1. So basically the analogy is the same as what the real servers had. So if we have any key associated to that in this spot up to server 1, so that's for the virtual node server 1, which basically translates to the real server 1. And this area up to server 0 sub 0 will end up going to server 0. So that's basically a simple analogy, but it is kind of extending it to the virtual nodes. It is the same as the real node. As the number of virtual nodes increases, the distribution of keys, okay, becomes more balanced. So yeah, as the number of virtual nodes, distribution of keys becomes more balanced. Yeah, of course, surely it becomes more balanced. But I guess if we kind of increase the number of virtual nodes so much, or that is too much, then the performance will reduce probably. But let's see. This is because the standard deviation gets smaller with more virtual nodes. That's the standard deviation is a probability in mathematic term. You could kind of search it on the YouTube and find what is a standard deviation and how it is kind of calculated, but it's not that much of a fancy word. Okay, gets smaller with more virtual nodes, leading to balanced data distribution. Standard deviation measures how data are spread out. Yeah, that's basically cool. The outcome of the experiment carried out by online research shows that with one or 200 virtual nodes, the standard deviation is between 5%, 200 virtual nodes, and 10%, 100 virtual nodes of the mean. So I guess it basically means like you would have 5 to 10% off of the balanced distribution. So you would be balanced like 90% of the time with 90% accuracy, but 5 to 10%, yeah, it's a bit fair trade-off to have. The standard deviation will be smaller when we increase the number of virtual nodes, which I said going too extreme on increasing the number of virtual nodes would be bad. However, more space are needed to store data about virtual nodes. This is a trade-off, and we can tune the number of virtual nodes to fit our system requirements. Find affected keys. Okay. When a server is added or removed, a fraction of data needs to be redistributed. Okay, so let's say a server is added, yeah, or removed from here. Okay, so a fraction of data needs to be redistributed. Yeah, I kind of can see that. Like, let's say a server. Before reading that, let's we ourselves kind of find an analogy. Let's say server 2 here, yeah. Server 2 needs to be added, so it is kind of added some. It will add some virtual nodes to that, actually, okay. But each time it is adding any virtual node, let's say, okay, like from now, here would be all the keys would be mapped to server 2. But now that the new server is added, so only this area before the new server needs to be recalculated, okay, redistributed. These keys are again, actually, they are already, not again, they are already distributed to server 2. So no need to redistribute these data. Only these data needs to be redistributed. But now imagine that we want to remove like server 0. Sorry about that. Remove this. So from now, previously, these data were distributed to server 0. Okay. Now that we removed this, so we need to remap all the data here up to here, the next server that we have. Okay, so only this data before this removed server needs to be redistributed, because the data after the server were already distributed to server 1. So no need to redistribute all the path, only from the path backward. And if we add something from the path forward, actually, if we consider, clockwise, it is backward. And we also add the server, so we go kind of counterclockwise. So, yeah, Okay, we could consider, okay, here, go back, and if we go this, here, if we go it this way, so I guess no matter we add the server or remove the server, we only need to redistribute the data from the point it is added or removed in backward order, okay? Not in the forward order. The forward is, okay. Let's now just read it. In figure, okay, a fraction of data needs to be redistributed. How can we find the affected range to redistribute the keys? Actually, we did. In figure 14.5, server 4 is added onto the ring. The affected range starts from server 4, newly added ones, and moves anti-clockwise around the ring until the server is found. Actually, we did that. You see? Anti-clockwise. That was the clockwise. Here, we went it this way, and we solved it. Thus, the key is located between server 3 and 4 needs to be redistributed to server 4. So here, server 3 and 4. So this one is added. So from here, going backward, okay, like this is the anti-clockwise. Only from 3 to 4 needs to be redistributed. When a server 1 is removed, let's say, I guess we would have it here. Yeah. If the server 1 is removed, as shown in figure 5.15, the affected range starts from server 1 removed and moves anti-clockwise. Again, see, we found the pattern ourselves. Moves anti-clockwise around the ring until the server is found, server 0. Thus, key is located between server 0 and server 1 must be redistributed to server 2. Actually, this is the same analogy. Like, we removed this server. So before that, how did we have the server keys? Okay, so we said from here, going clockwise, all the keys are mapped to server 1. All right, now we only remove that. So if we remove that, so let's see. If you remove it, these keys are already distributed correctly to server 2. Only the anti-clockwise of that needs to be redistributed to the ones that are already distributed to the correct server. See that? So that's the same pattern. So now the wrap up. In this chapter, oh, that was a fairly short video compared to the others, like this is 42 minutes. In this chapter, we had an in-depth discussion about consistent hashing, including why it is needed and how it works. The benefits of consistent hashing include minimized keys are redistributed when servers are added or removed. Minimized keys. Let's say it again. The benefits of consistent hashing. Minimized keys are redistributed when servers are added or removed. See? Only this area are redistributed, minimized keys. Okay? It is easy to scale horizontally because data are more evenly distributed. It is more, why? Because of the virtual nodes. Okay? The virtual nodes take care of inconsistent hashing. So it takes care of unbalanced distribution. Yeah, not inconsistency. Yeah. Mitigate hotspot key problem. Excessive access to a specific shard could cause server overload. Imagine data for Katy Perry, Justin Bieber, and Lady Gaga all end up on the same shard. Okay. Yeah. Consistent hashing helps to mitigate the problem of distributing the data more evenly. Yeah. More evenly, but again, these problem could happen. Probably, we could kind of have, yeah, if we have like 100 really hotspot celebrity, so we could evenly distribute them and also have this kind of algorithm. But anyway, it depends on the problem. Consistent hashing helps to mitigate the problem by distributing the data more evenly. Consistent hashing is widely used in real-world systems, including some notable ones. Let's see. Partitioning components of Amazon's Dynamo database, DynamoDB. Okay. The data partitioning across the cluster in Apache Cassandra. Yeah, nice. And the Discord chat application. Yeah, okay. It means just all the chat apps are slow, not just one of them. Akami Content Delivery Network, CDN, and Maglev Network Load Balancer. So congratulations on getting this far. Now give yourself a pat on the back. Good job. In the next session, so these were the references of that. In the next session, hopefully, we will get into the chapter 6, design a key value store. This was really nice for me because at first I didn't get what the ring analogy is, but in some spot I just kind of had aha moment. Aha, I'm getting it. So, and the rest of it, we just read some part of the text and we kind of analyzed that and we found out how could it be so, and it were. So, but as far as you see, these are just the pictures and drawings. The implementation is the key actually here. We could just talk about different drawings for long hours, but it will boils down to the implementation. So at least for me, unless I do not implement these ideas, I don't consider myself a system designer. But anyway, take care of yourself, guys, and have a nice day. And I genuinely appreciate that you have come this far. Thank you and goodbye.